Assalamu alaikum wa rahmatullahi wa barakatuh. Today we're going to explain the average shear stress. So our objective is to explain the concept of average shear stress. In the last lecture تعرفنا على normal stress. الnormal stress قلنا أو average normal stress we represent it with sigma and it's equal to the normal over الarea. الافريج shear stress ما هو مرة مختلف عن السيجما بس we represent it with tau and it is the shear stress over the area. Okay. However, in the shear stress we have three types. We have the first type, which is the single shear, and we have the double shear, and we have the punching shear. Okay, so the normal stress قلنا إنه دائما يجي normal للarea يعني perpendicular. However, the average stress يجي parallel because it resists sliding. So what is the meaning of average shear stress? It's the stress that resists the sliding. So here as you can see that we have three types. So first of all, we will look at the single shear and it looks like this. So in the single shear, usually the resistance of sliding across its single cross-sectional area ويكون between two plates. يعني يكون فقط area واحدة that is resisting a sliding, so we call this single shear. And the equation will be the same. T average is the shear force over the area that is being subjected or the area that is resisting sliding. If we will look here, where is the area that is resisting sliding? It's the area of the bolt, which is this. That is the area which is resisting sliding. However, here, those two plates are glued together. So which area is resisting sliding? It's this, the whole area. So حنا عندنا يعني ال two plates usually يكونون attached to one another either by bolts or they are glued as in this example. So the area which resists the sliding, we will consider it to be the area that we will divide the force عليها. And the force is this one, the force applied. So you will take this force divided by the area. So the shear force is equal to the applied force, and by that we get the tau average. So now we are done from the single shear. Now let's look at the double shear. So in the double shear, it resists shear across two cross-sectional areas. As you can see here, we have the three plates. 1, 2, 3. So whenever you have the three plates, here we have double shear. Here the same thing. We have three plates. So which areas are resisting sliding? It's this area and this area. They are both resisting sliding. So if we apply here force, the shear force is going to be half in this plate and half in this plate in order to be in equilibrium. The same thing here. The area of the bolt over here and over here. If we are applying force F, the shear force is going to be half of this because we have to equate them. فبيكون هنا نص وهنا نص. So this will be equal to F. If we sum F half, F half. So these are an example of the bolted steel joint in double shear. And V is equal to F over 2. Also here, F over 2. So now we are done from the second type of the shear stress. Now we will go to the punching shear. So the stress along the internal surface of a hole in a plate made by punching out a slug is shown in the following figure. is known as a punching shear. So punching shear يعني زي نقول قاعدين ندفع أو نحاول it's resisting sliding in this area هذه. فهير this area will be equal to the circumference times the thickness. So here the punching shear stress force is gonna be يعني هو نفسه ال P ولكن ال area it's the length the thickness. Length is the perimeter or circumference of the puncture. Here is an example توضح أكثر ال punching shear. If we are applying force P and we have the thickness of this square is 25 millimeter and we are given that the circumference is 20 or the length. So this one is the radius, I guess. No, this one is the diameter because the circumference is 2 pi r. So خلاص pi d is also equal to the circumference of the circle. So here it is. 20 is the diameter and pi, we calculated the circumference, multiplied it by the thickness in order to get the area, which is this area. That is resisting sliding. Okay, now we will have a look at this example. It says determine the average shear stress in the 20 millimeter diameter pin A and the 30 millimeter diameter pin B that supports the beam. So here we have a zoomed out picture of pin A, and here we have a zoomed in picture of pin B. Here we have 1, 2, 3 plates. So in pin A, we have double shear. However, in pin A, the area which is resisting sliding is just this. So in pin A, in pin B, we have single shear. Okay, now what do we need to find? We will go back to the internal loading lecture and we need to find the resultant force. So here, let's first of all start by drawing the free body diagram. And at 2 meters over here, we have an external loading of 30 kilonewtons. And here, this one is 4 meter. We have a tension force, and I will call it force, two force member of BC. And the dimensions are given, 5, 4, and this one is a 3. Okay, here, this one is a pin or hinge, so it resists the motion in the vertical and horizontal direction. So we have AY and we have AX. Now it's very important that the shear in this pin A, is gonna be equal. So FA is gonna be equal to AX squared plus AY squared. We're not just gonna take the Y alone or the X alone. Now we can start by summing the moment around point A. This one is minus 32. And this one is FBC. Okay, we are not given this. Okay, FBC 4/5 and the distance is 6. So we get FBC as 12.5 kilonewtons. Now we will sum the forces in the y. AY minus 30 plus 12.5 . So AY is equal to 20 kilonewtons. Now we need to sum the forces in the x direction. It's minus AX plus F, or 12.5, which is FBC, 12.5, 3 over 5. So AX is equal to 7.5 kilonewtons. Now I need to find the resultant force at pin A. Which is 7.5 squared plus 20 squared. Okay, now we have all the information that we need. So, first of all, let's start by pin A. In pin A, we said that we have double shear. So V is equal to F over 2. Now what is F? It's a 21.36 over 2. So the shear in pin A is equal to 10.68 kilonewtons. And the area of A is 20 squared. So my total shear at A will be equal to VA over area of A. We need to convert this one طبعا إلى Newton, so multiply it by 1000. So the shear at pin A is 33.99, approximately 34 megapascal. Now we will move to pin B. In pin B, we said that we have single shear. So in single shear, V is equal to F. So what is FBC? It is 12.5 kilonewtons. And the area of B, the diameter is 30. So 30 squared times pi over 4. So the tau average at B, or the normal shear, the average shear stress, is equal to 12.5 over the area, which is this area. We get it to be 17.68 megapascal. Okay, for this example, the yoke and the rod connection is subjected to a tensile force of 5 kilonewton. So we need to determine the average normal stress, which is sigma, and we need to determine the shear stress in pin A. Okay, so for this one, I'm gonna call it rod 1, and this one is rod 2. So sigma in 1 is equal to 5 kilonewtons times the area, which is 40 squares times pi over 4. Here we get it as 4 megapascal. And in the second one, it's gonna be the area, which is 30. So we will have it 7.07 megapascal. Now for the shear stress in pin A, we have double shear, because as you see 1, 2, 3 plates, or 3 areas that they are resisting and sliding. So the V, or the shear force, is going to be equal to half of the force, which is 5/2, so that is 2.5 kilopascal. So tau in A is 2.5 kilopascal over the area, and here we are given the diameter. So the average shear stress is 5.1 megapascal.